Hello, I'm Tyler Hague. I'm experimental ISCR fellow at Jefferson Lab, and I was asked to give a lecture, seminar, whatever it's called. I don't know the difference between those things, about the proton radius experiment, PRAD, and I'm going to start with background of what the proton radius puzzle is. So like, why do we study this and all that sort of stuff. So for context, PRAD-2, the second iteration of the proton radius experiment, is currently ongoing in Hall B. I say currently, I guess we don't have beam right now because they're doing a scaling of the machine energy, but we're in the middle of the run period and we got a lot of data, and that's pretty cool. So my slide will advance. So yeah, we're going to start with the proton radius puzzle to set up why we even measure this, why we study it, what's interesting, useful. So first question, what is the radius? Adam was talking before about these pressure forces, and I caught that he mentioned a gravitational radius, and this is different from that. Here, we are talking about a charge radius. So I am speaking out of order because I forgot I put this here. So what is the proton radius? 0.84 Fermi, femtometers. And that is according to NIST, CODATA, PDG, et cetera. That's slightly contested value, maybe not so much as it used to be, but that's what I say it is, and so here we are. So what is the proton radius in reality, though? We have a number. So it's probably more accurately stated as the root mean square charge radius. So we have some charge distribution from your quarks, your C quarks, all this other junk that's moving around inside your proton, and how far does that charge reach? How far away can you see it? And so it's related to this non-relativistic charge distribution. I put here, if I can, there, that's the laser button. Referencing this paper by Jerry Miller that explains what it is and is not. Oftentimes we'll talk about it as being related to these transformations of the charge field and whatnot, and I'm an experimentalist, and experimentalists will simplify it, and the theorists will tell us when we're wrong. More accurately, but maybe less satisfactorily, it's fundamental property of the first derivative of the Sachs form factor when you evaluate it at 0 for momentum transfer. So as I call it, the non-scattering limit, because if you transfer 0 for momentum, you didn't scatter. And I can't advance with that. So what is the proton radius puzzle? At one point in time, we thought that it was 0.88 femtometers. Previously, I said it's 0.84, and then it wasn't. In 2010, this group, Pohl et al., published this Nature paper that found a 0.84 femtometer radius, and that was a 5.6 sigma discrepancy with the previously accepted value. Because it was so precise. They used this muonic hydrogen technique that gave them unprecedented precision as to measuring this. And so ever since then, we've been trying to understand who's right and why are we getting different numbers. And why should you care? Maybe only parents are going to get this reference. That's Bluey TV show, one of my kids' favorite shows. This Unicourse pops up all over the episode and says, "And why should I care?" So there's a lot of interesting things that this can touch on in a variety of places. So there's questions of, well, maybe the difference is new physics. The smaller value was first seen with muonic hydrogen. So could lepton universality be violated? Because every other measurement used electrons. Muse is studying this at PSI. They're using electron, positron, and positive and negative muon beams to measure this to see if there's any systemic difference between the two lepton species. There's a question of inconsistent definitions. Perhaps this spectroscopy measurement and electron scattering measurement had two different definitions that weren't actually the same, even though we thought they were. That's been disproven. That paper that I referenced before goes through a lengthy derivation to show that they are studying the same thing. One of the things that's popped up a lot is, are we just extracting it poorly? To extract the radius, we have to extrapolate by definition. And so your choice of fit is going to impact your extraction. And maybe we're just really crappy at fitting. Another question is, maybe we have the Rydberg constant incorrect. That is the most precisely known fundamental constant that we have. And in part due to this puzzle, that value was updated by CODATA in 2018. It doesn't resolve all of the discrepancies, but it is a piece of the puzzle and how it has impacted our knowledge of physics. So how do we measure it? There are two dominant ways. We've got electron scattering, which I don't talk about too terribly much on this slide, because that's the rest of my slides, because that's what I do. But you have an electron, or well, any lepton goes in, hits your proton, elastic scattering off of it, and you need to measure at extraordinarily low Q squared so that you don't bias your extrapolation too terribly much by extrapolating really far. And then there's the hydrogen Lamb shift, which you have the excited states. You take your electron, excite it to a new state, and then that energy decay is sensitive to that Sachs form factor. And the difference between those energy states is very little. So that gets you to extraordinarily low Q squared and gets you a much more precise measurement than electron scattering. But if you have different tools, you want to make sure that they agree. That's the tool should not give you a different answer, and we want to understand why. Radiative effects are also very small. Muonic hydrogen is what kicked off this puzzle with giving a much smaller value than electron spectroscopy. And so real fast on the spectroscopy measurements, we have atomic hydrogen spectroscopy, which was how it was traditionally done, where your energy shift in the hydrogen atom is related to the proton finite size effects. And all that means is your proton is not a point particle, so the energy shift is sensitive to how big it actually is. The interaction is dominated by your electromagnetic force, so you get your electric form factor, and it is more or less directly related to the first derivative of the form factor at Q squared of 0. You can just get that by a Taylor expansion because you are so close to 0, which then gives you your proton radius term immediately. And historically extracted 0.88 femtometers. Some recent, like very recent measurements have gotten 0.84. We still don't understand fully the discrepancy there, but that's a spectroscopy experimentalist's job, not mine. But then what happens if you replace your electron in this spectroscopy measurement with a muon? Muon is 200 times heavier than your electron, so it's going to orbit a lot closer. The difference in energy between those levels is going to be way smaller. You get a much higher sensitivity to the proton finite size effects. And so you get an extraordinarily accurate measurement, way more accurate than you get with the electron. And it's a cool technique that has created problems for all of us. So now, electron scattering. This is where we're going to sit for the rest of the talk. Done with spectroscopy because I'm not good at it. So I think most of the talks in CNUGS are theory-based. There are some experimental talks I saw, but one of the things that I talked with Alberto about when talking about what I could present in this talk, we said it would be useful to talk about how do you actually design an experiment? You say you want to measure something. How do you then take that, I want to measure this, to how do I do it? And so I kind of envision this being semi-interactive. We'll get to that in a minute. But what do we need to measure? We need to measure proton radius. which is -6 times the first derivative of the electric form factor evaluated at q squared of 0. How do you get that electric form factor? Through scattering. You go with your elastic electron-proton scattering cross-section, and it's related to, you got your Mach cross-section, all these other kinematic terms, your electric form factor, and also your magnetic form factor. So you have to figure out how to get from this to your electric form factor. And you've got all these other things that you can plug in, q squared, tau, epsilon, Mach cross-section, and so we need to measure that, and that button's no. And once you've decided what you need to measure, you then also need to think about what your experiment needs to do. You need particle identification. What particle actually went into your detector? We want electrons. Electron hits proton, electron goes out. You want to catch that electron. That can fully define your q squared. You want an energy measurement. You need that you need the energy of it to define q squared, and you need the angle of it. You also want to identify and mitigate backgrounds. If you have a background that mimics what you're trying to see, then you're going to get the wrong answer if you don't deal with that. You want an experiment, a setup that's going to create minimal background itself. So you don't want to have your electrons going through a whole bunch of excess material and rescattering and really throwing off their angle, throwing off their energy. And you know the luminosity, which is basically how much beam did you throw at a target and how big is that target? These are all things that you need to understand. And so what are your ideas for this measurement? And then we'll go to what PRAD did. So we need, where'd that pointer go? We need the slope of GE as q squared goes to 0. We need to deal with the magnetic form factor. Need to think about backgrounds and luminosity. I threw up q squared here so that we can talk about, it's pretty clear how you get to 0. You've got 3 lever arms, E prime, theta, E beam energy, E prime, scattered electron energy, theta being angle. And so we want to get q squared as low as possible. So keep expecting that to work. So if we've got these equations, how would you think about getting towards extraordinarily low q squared, getting GE out of here? Any ideas that you want to throw out there?
Expand around q squared is equal to 0 or something like that and see if we have like a good analytic.
So that is a great point. You're saying, is there an analytic expression for GE? And that is a massive pain point in that there is not.
Okay.
We have no analytic expression for GE, so we have to do our best to fit and hope that we didn't bias the fit with what we chose. But what would you want your spectrometer to look like, maybe?
Can we like I was thinking like we could change the value of tau by epsilon and fit the fit those with 2 different GE and GM to extract them.
Yes. So you are talking about like a Rosenbluth extraction.
Yeah, that's what I'm talking about.
Yes. So that is where you've got your cross section, and pretend that looks like a sigma. And if you then have different, no, not different, not q squared, that's epsilon. You have it at different epsilon, you can then measure at some q squared, so epsilon goes from 0 to 1. You could then plot a few points, and the relationship between the reduced cross-section, where you divide out all those kinematic terms at the front, is linear between GE and GM with respect to epsilon. And so you can then fit a line and you can directly get out GE and GM. That is a technique that is commonly used. So what I'm envisioning with this thing is we're going to talk about what's good and what your trade-offs are, because when you're making a measurement, everything has a trade-off and you just got to decide what you're willing to live with. So the pros, you get GE, you get GM, you're not reliant on a model. This is a completely model independent extraction. The difficulty is you generally want more than 2 points. 2 points defines a line, but you also are going to have statistical scatter. You might have systematics. You want enough points that you can then do this and draw your trend line between them. But each one of those points needs a different beam energy that then is going to be at a different angle so that you get the same Q squared. And that is good if you can do it. It's very difficult, and you need to understand all of your beam energy systematics well. You need to understand your angular measurement very well. I like this technique. I would probably do that if I were designing an experiment, because I have proposed one for something else doing it that way. That's not what we're doing in PRAD. But yes, another group has done that. Any other ideas? Yes.
Maybe you would like to have an acceptance that maximizes the statistics of the mod cross-section.
Yes, so you want to maximize your statistics.
Right, so maybe, would it be like a small angle?
Yes. And that is what ERAD did. So if we go to a small angle, what you get is you maximize your Mott cross section, which is good. You get your statistics a lot faster, which is very helpful. One of the other side effects of that that's actually extraordinarily helpful is that then this tau over epsilon piece goes to extremely small. You have then made you've made the contribution of the magnetic form factor very, very small. So if you don't do this with your Rosenblum separation, you instead can say it's small. You can use a model dependent extraction, but because it's such a small correction, that uncertainty from the model choice doesn't impact your total systematic uncertainty very much. Other difficulty with that, though, is there are a lot of backgrounds at extraordinarily small angle. So you have to then be very good at separating those out and be very careful about how you treat those backgrounds so that you don't muck up your data. Any further thoughts? Yeah.
Can I ask a question?
Yes.
So how do you do in this case the electron tagging, considering that it probably has a very small angle? So how do you differentiate it, the electron that is scattering with the electron from the beam?
Good question. So before I answer that, because that'll be jumping into what PRAD did, does anybody else want to talk about any other ideas before we move on? I promise we will get to that. It's like next.
We measure, if we know the given beam energy, measure the frequency, maybe?
The frequency. What do you mean by frequency?
Like if you know the given energy and given beam energy, then after scattering, what happens? The difference in the energies.
Oh, okay. So the probability of different energies. So that is, yes. So that functionally is the cross section, which is what we want to measure. So the cross section is effectively the probability of scattering at given kinematics. That's a oversimplification of it, of course, but I'm an experimentalist, so. Anything else, or we will move on to Peter? Did you? All right, let's talk about what PRED did. So, and note, I am meaning PRED 1, so the first experiment. We'll get to the second one shortly. So what did PRED do? So for particle ID, there's a couple of different things you can do. First, electron-proton scattering for elastic scattering is an extraordinarily well-defined kinematic. You have proton and electron in, proton, electron out. That energy conservation, you can get an exact value. If you put a restriction on where that electron was bound, then you can put a cut window around that energy and say that if it was there and it had the wrong energy for elastic scattering, clearly it didn't originate from elastic scattering, and you can throw it out. And so that gives you your that's how you say that it's something you want to measure. It's an electron. The other way to check that it's an electron is we have these gem planes. Gems only give you a signal when a charged particle goes through it. Asterisk there. Sometimes that happens with a neutral particle, and we call that an inefficiency. But we're pretending we have a perfect detector right now. So gems only detect charged particles. So if you have a hit in your calorimeter back here, which is energy measurement device, and it doesn't have a corresponding hit in your gem, then you can say that's not an electron, it's not charged. For the energy measurement, we then have this calorimeter in the back. So we call this HiCal, that's short for hybrid calorimeter. Hybrid meaning that there are two different types of crystals in it for measuring the energy. So these are crystals that when the electron goes in, it starts depositing the energy. It then creates light, and that light creates then a shower that's picked up by photomultiplier tubes, converted into an electrical signal, and off to your computer for analysis. So we have two different types. We have lead tungstate, this PbWo4, in the most central region, so the very, very small angles, because that's where we want to, we're wanting to get to low Q squared. Small angles is where low Q squared is at. We want our most precise measurements there. Then surrounding that, we have lead glass flux. The reason for that is, as I was saying before, every design choice has trade-offs. Lead tungstate are what we want for the high resolution. Lead tungstate crystals are extraordinarily expensive to fill up the rest of that calorimeter, which we do want that full acceptance, would have been astronomically expensive. So we went with the lead glass option, which gives us an energy measurement. It's slightly less precise, but it still gives us a useful measurement. For reference, in 2022, I want to say, I helped work on a proposal to try and get money to upgrade the rest of the calorimeter to lead tungstate. And at the time, we realized that we hit the maximum that we could ask for, which was 8 million, and that would only upgrade 2/3 of it. So we, that didn't happen. So tracking, again, this gem plane, one benefit, charged particles are the only ones that are going to give you a signal. Another benefit, this is just an extraordinarily high resolution tracking device. We get ours from a team over at University of Virginia that builds them, and they're like gurus at it, and it gets you extremely precise tracking with very good efficiencies. So you're going to catch most of it. Identifying backgrounds, we do that with, as I said before, the kinematics are very well defined. So we require that the energy and angle match what we would expect for elastic scattering. Minimizing backgrounds, this one is an interesting thing. We have here this vacuum chamber. So what happens is we have our electron coming in from the beamline here on the left, and it goes into our target chamber where we have hydrogen, our proton target source. But then going to this tracker and calorimeter, we've got this big vacuum chamber. This is, I believe, 5-ish meters long. And we pump that down so that you have very little chance of those electrons hitting something along their way and throwing off their energy, throwing off their angle. This is maybe a ES&H nightmare, because vacuum chambers are, I guess, functionally mini bombs. But then for measuring luminosity, this is the other thing that we want to do. So Hall B doesn't have beam current monitors like maybe Hall A and Hall C has. That's where those are where I do the bulk of my work. Instead, they have a Faraday cup, but that's not the most precise tool. So instead, for measuring luminosity, we can use molar scattering. So that's electron from the beam goes in, hits an atomic electron from that hydrogen atom and scatters. And that you can exactly calculate that cross section from QED. You don't have to deal with any of the QCD stuff that mucks up your calculations. You can exactly calculate that and then detect it and then normalize to it. The only kind of difficult thing is when you go to extremely low scattering angle here, you see that this electron-electron scattering and electron-proton scattering bands really start to converge. And if you're only detecting one electron, that becomes a problem. So we had to kind of cut off our analysis right about here because we decided they were overlapping too much and that gave us way too much systematics that we didn't quite trust the result. Yes.
That's a small question. So looking at that graph, he seems to like change at about 3.5 degrees there. Is that because of the lead calorimeter blocks there?
Yes.
You have the better ones sort of more forward?
Right. Yes. Yes. The range here at low angles where you have much smaller bands, that's where you have your lead tungstate crystals. And in the where the larger band is, those are your lead glass crystals. They have lower resolution for your energy, and that's why you have to kind of take this wider chunk. Forget to write text on this. I was supposed to say other scattering stuff, or well, other scattering measurements since the puzzle started. So the other one that happened, this was before PRAD, but it's the other one that gets talked about a lot because we use it as a point of reference for, reference is the wrong word, point of comparison with PRAD of trying to really wrangle, do we understand electron scattering, proton radius measurements? So this happened in MINES company. They used many overlapping data sets. So they had this kind of 3 spectrometer facility for the A1 collaboration. And they had electrons coming in, hitting a hydrogen target, and they could detect electrons at 3 different angles at the same time. And then they would rotate these around to collect different Q-squared kinematics. And each setting would have overlap with some other setting, so they could then make sure that they understood the luminosity relative to each other setting. And that gave them this kind of normalization check. They then had this huge Q-squared range, and they got a large radius. So that's one of the things that when I say 0.84 is generally accepted, but not fully, it's still contested. That is partially because A1 and PRAD got different results, and we are still trying to figure out why. And then keep using that button. One little more blurb about PRAD. A lot of this I said already. We didn't have a magnet. We went very far forward. Windowless gas flow target to minimize background. 2 beam energies. There wasn't enough overlap to do like a Rosenbluth separation like we talked about. There's a small overlap, but it's also when you're very far forward, you have epsilon very, very close to 1 for both measurements. So you don't have any lever arm. So imagine you have this Rosenbluth plot and you, if you have 2 points right here and right here, and they have error bars like this, your line that you draw through it can go from, you know, here to here, and you have basically no sensitivity to extracting this, so that we have two beam energies, but we couldn't do that. Anyways, PRAD got 0.83, so much more in line with the small radius that hydrogen, or not hydrogen, muonic hydrogen measurements got. And so now you might be saying, you know, is the puzzle resolved? PRAD got a small radius. A lot of spectroscopy measurements have gotten small radius. We have this outlier. That's too strong of a statement. We have A1 that got a large radius. But generally, people are trending towards a small radius. Most experiments are getting that. Is it resolved? It's kind of getting there, but it's not definitive, and we need new data and techniques to back it up. And so the reason why, like this is the state of the radius puzzle shortly after PRAD. You can see CODATA revised their radius to the small one. PRAD got this measurement. A1 got this measurement. And all of the newer measurements are really trending to the small side. But current state of it, things that are still open, you know, we've reanalyzed past data, seems to support the small radius, but it's not, there are explanations, but they're not terribly conclusive. Still unknown for the spectroscopy. And what don't we know? Is the Rydberg constant correct? We've updated it. There's some hypotheses that maybe it's still a little bit off. I don't think that is as strong of a thought as it used to be, but it is something that I periodically will see pop up in the literature. There's questions about lepton universality. These two, we can't really do anything about that with PRAD. We're not doing spectroscopy, so we're not sensitive to the Rydberg constant. We've got one species of lepton. We can't test universality, but there is a form factor discrepancy between PRAD and A1. And so that's why we're doing, well, part of why we're doing PRAD 2. And so motivating this new measurement, we have this discrepancy. So here you have in the red points are the original PRAD results. These black points are the MINES A1 results. And you see this systematic shift. MINES has a lot of points, but one thing to caution, because you may look at this and say, okay, that's a lot of points that show a clear trend with smaller uncertainties, especially if you were to fit that. The MINES extraction is a little bit more model dependent. Their results required a magnetic form factor input and were not at small of an angle as PRAD were. And so the systematics from the magnetic form factor contribute substantially more. That's not to say that it's wrong. That's just a caveat that has to be said, is that there's perhaps more model dependence to that than PRAD, but that also doesn't mean that PRAD's right. That's up for debate and why we're doing another experiment. Both sets have similar precision. And so PRAD 2 really is aiming to get the radius at very small q squared, but also remeasure this region with a lot more precision in hopes that we will understand it better and resolve who got it right. And so there's also been, I saw the last bullet and realized I've skipped over this. This MINES jet data, there was a follow-up experiment at MINES using a hydrogen jet target. So whenever the electrons were coming in, they would send a puff of hydrogen in, so they really understood how much target they had. And that is a very low statistics measurement. Or low statistics is the wrong way. It takes a lot of time to get statistics, and so they only have a few data points. And this plot is actually pulled from their paper, which was saying that they can align their data both with PRAD and with the A1 data and it agrees to similar chi-squared, and the model allows that fluctuation. And so they basically said, well, we can't use this technique to resolve the discrepancy. We need to do it again a different way. And the other thing that PRAD2 aims to get is a more precise normalization. So fits to data include a normalization parameter for each data set. Mine's A1 had 31 normalization parameters, I want to say. PRAD had 2 because we had 2 beam energies, 2 data sets. Those normalization parameters give you internal consistency because you want your 2 measurements at the same Q² to agree. There's no reason they shouldn't when you're looking at this GE parameter. Cross-section depends on the beam energy, but GE should not. GE is defined as 1 at Q² of 0, so that gives you kind of an anchor point when you're doing your fitting, when you're trying to assess your normalization. And if we go closer to the limit, we can really just better constrain our normalization of the data over that entire Q². And so that's what the Mines gas jet target experiment did. And unfortunately, we're incapable of solving the discrepancy. And so here we are with PRAD2. So PRAD2, we want to do it again, but better. And so thinking about how PRAD1 was designed from the slides before, what were the trade-offs and what could we, this is again intended to be interactive, what could we do to improve on this? Are there any, if we think about doing an experiment like PRAD in pretty much the same fashion as PRAD, but we want to do it better with, maybe we can do some updates to the spectrometer, what could we do to make it better? Leave your hand was up first.
Yeah, this was going to be a question, but maybe ties up with this interactive part. Because there you show the reconstructed energy as a way to tag the EP event. But also I imagine that the delta phi distribution of this pair has to be very characteristic because it's a elastic event. So that is something that you look at PRAD1 or are you going to look at PRAD2?
So no, we did not. For electron proton, no, we did not. The proton at this such a small 4 momentum transfer is not really going anywhere. It's not going to make it to your calorimeter through your GEMS. You're not going to detect that proton. For the electron-electron scattering, for some of that we can. Not all of these kinematics, since that's a well-defined kinematic, your some angles that second electron will be within your acceptance, some of them they won't be. Now, we can't take our energy measurement based on the 2 electrons and say that that must sum to the beam energy. That's one rabbit hole that you might get interested in going down because that will give you your beam energy. But then because you are hinging your analysis on detecting 2 particles, you have then made your systematic uncertainties very different from the 1 particle detection case of the electron proton. And if we want to normalize to this, we need to make sure that our systematics between them are functionally the same, like the efficiencies of the detector. Because any inefficiencies are going to compound into your systematics if you're trying to detect 2 things. You can do tagging though. That's where you say, we detected it, so we understand it, but we can't use the energy measurement of this thing. It tells us that we got it right.
More lead tungstate.
I wish. Don't have that kind of money. That is something that we, as I referenced before, that we did try to do. The money just wasn't there. It's actually kind of interesting when when PRAD 2 was proposed, that was one of the things that they said we're gonna do. And there's this table at the end of the proposal that says, all of these upgrades that we're gonna do, here's how they will improve our systematic uncertainty on the final answer. And when we got told no for getting the money, we took a look at it and we said, okay, well, this is the most expensive upgrade for the least systematic improvements. So we kind of dropped that. Yes,
What target did PRAD 1 use?
hydrogen.
But like,
Oh.
was it in like a?
So we have this cell right here that is really cool, and our target group did a whole lot of work here at JLab to make this happen. So what this is actually is you have normally in like halls A and C, you'll have a cryo cell, which is this aluminum cell that has material on the front, material on the back around it that encases your gas target. And your electron beam goes through it, but then you have to subtract that aluminum from your result because you're going to scatter from the aluminum as well. It's thicker. Here, what we did was I keep saying I wasn't involved with PRAD 1. I'm only involved with PRAD 2. I should caveat that, but the target was in here, and this chamber right here is in the middle of this. And so hydrogen is pumped in, and if you stare really closely right here, you can see a little circle in the middle. That's where the beam goes through. The beam actually does not go through any target cell material, so we're constantly flowing hydrogen into there. And then the hydrogen flows out, and there are pumps immediately outside of that to then pump that hydrogen away from the beam so that you're only scattering from the hydrogen that's in here, and you have a good understanding of how much hydrogen you have by measuring temperature and pressure.
Yeah, so there's already no like total back then. But
Something that was mentioned earlier is that you had two different energies for PRAD, but they were very close together. You couldn't really do a good fit from that. Is PRAD 2 going to have the ability to go with a
Unfortunately,
wider energy range or no?
unfortunately, no. So we will have 3 beam energies, but epsilon here is extremely sensitive to angle. And so because PRAD, the spectrometer, does not move. It is fixed directly in front of the beam. We have a little, I think, I want to say 4 by 4 centimeter square in the middle where the beam can pass through. And the angles that it's set at are the angles we got. And because of that, at least at energies that JLab can give you, you have no epsilon lever arm. You're just always going to be basically at 1.
Am I right in understanding that the functions that you're fitting functionally are exponential or decaying exponential, or what are they?
That is a good question. No, they are not a decaying exponential. We will talk about fitting functions very shortly. I have a demo with that, and we can even play with the decaying exponential. That's not what we used, but that's a great question.
I also had a question about operating at like different energies. Is it the case that it is not preferred having multiple different energy data points because all of these things are model independent, and like the question of like overfitting, like does that become a concern, or is it mostly hardware that we're limited with like a certain set of energies?
So it's largely hardware-ish that limits the energy in that because the spectrometer can only be in one spot, the energy completely defines your Q-squared acceptance. And so if we want to go to low Q-squared, we got to go to low energy. If we go to higher energy, we're just not going to get the low Q-squared part. That will give you something that you can then say, okay, well, at the same Q-squared, the electric form factor should overlap with the electric form factor from a different energy. And that does actually help you out with fitting. You want to capture any moments at the higher Q-squared. but the accelerator does not like to change it too terribly often. In general, because we are one of 4 halls running at any given point in time, we have to choose energies that are compatible with the other experiments receiving the beam energy that they need. And so if nominally JLab CBAF gives you 2.2, 4.4, 6.6, 8.8, blah, 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 blah. For PRAD, we did 1.1 and 2.2. So that 1.1 is an off standard beam energy. And so that then limits what other people can get because we have to then scale the machine so that it can deliver that. And if we wanted to do a whole bunch of really very low energy just to get to low Q squared, then we've really made, I think you met Doug on the second day, maybe the first day, we've made it very much a problem if we ask for a whole lot of weird energies because he has to figure out how to schedule that and make everybody happy.
More ideas?
All right, so let's keep on going. So what did PRAD2 actually do? And we did, so first thing we did was actually 2 gem planes. So PRAD1 had 1 gem plane. PRAD2 has 2. Reason for that is, if there's an inefficiency with one, then you've got a second one. You have a second chance of catching that electron. And if you just require that one hit, then you're golden. You've just upped your efficiency. So you have lower systematics, you get your statistics faster. Also gives you improved Q squared resolution. So Q squared, as we showed before, 4 times E prime sine squared theta over 2. You need that angle very well measured. You need the energy well measured too, but if we're thinking about the angle, for measuring the angle with PRAD1, you have your gem plane and you have your calorimeter. Those two are very close together. You don't have a whole lot of lever arm. Here, the gems are still close together, but the calorimeter doesn't have very high resolution. Each of those lead tungstate crystals, which are the high resolution ones, those are 2 centimeters by 2 centimeters. So you could say that it was in this 2 centimeter by 2 centimeter window, and then it has to go through the gem where it hit there, and then you just project it back to the target. But that doesn't give you a whole lot of resolution. If you have 2 very high position resolutions, you can draw your line back to the target a lot more precisely, and you get just much better position resolution, which is directly your Q squared improvement. Another thing that we did, upgraded the DAC readout. So that's the electronics. We were talking about the spectrometer a lot. Another piece of this that maybe doesn't often get talked about, and I probably should have talked about it sooner, but I forgot. All of your components have to be routed to where that data then goes to a computer, processed, written to tape, so that then we can go sit at a computer and analyze it later. When you're extremely forward angles, we said background is extraordinarily high. So you're getting just a whole lot of crap thrown at your detector that maybe you don't want to record. You need something that's able to survive that. If you have a signal that comes in, your electronics have to process, does this signal matter enough? You write it down. And that creates what's called dead time. While it is deciding if it can write down that event to the computer, you can't record anything else. It can't process something else. So we need stuff that's faster, which this was an upgrade. Also, with some really clever techniques that don't ask me to explain them because I didn't do it and I couldn't do it. Improved electronics also gave us real-time cluster finding. So whenever an electron hits this calorimeter, it's going to go in and deposit that energy. We said, deposit the energy, creates light. That light disperses. It's not all contained to that single crystal that it hits. So you're going to get a little bit of energy in that one, a little bit in the ones next to it, maybe a little bit bigger. If you can then really say, okay, we found this cluster, this is our electron. These blocks gives us our electron energy. You can then say, well, does it match what we should expect it to be given where that block is? And that analysis is crude at that step. You're not going to do as tight of a cut as you would during your final analysis, but you can still put a cut and throw away a whole lot of junk. And so you're going to write down a lot less. You're going to keep your electronics alive more so that you can record more of what you do want to record. And it's a very cool upgrade. And then the other thing that we almost touched on, but just barely skirted around it, is this new scintillator detector. So we talked about this overlap of EE and EP event at very low energy. And we said, okay, well, we don't measure that second electron because that throws off our systematics, but we do tag that second electron when we can. And that allows us to say, is it EE or is it EP? Because that second one has to be at a well-defined angle. You ideally would want energy, but that's kind of difficult. Scintillators give you angle at least very well. And so right around the target, we have our target right here. Right in front of it, we have this new scintillator detector, and these can rotate in and out of the plane of scattering. And so when you go to really low angle for the electron that you're detecting for molar scattering, that second electron goes to larger and larger angle. And that's when it starts going out of the acceptance of your calorimeter, but it can still be where you detect it with these higher angle scintillators. Scintillators are very fast. They give you timing. They give you kind of crude tracking, depends on how big the scintillator block is. It gives you particle ID because scintillators, like GEMS, only fire if it's a charged particle going through it. So this allows us to tag these molar scattering events to even lower angle so that we can recover this data and then use it for the analysis and get to even lower Q squared. And so all of this, this is what we're doing right now. So we have 3 beam energies. We have 0.7, 2.1, 3.5, revised the 2.1 to 2.2. These are old slides that I copy pasted for today. We did 0.7 and 3.5 already. We are down right now to rescale the machine to 2.2 so that everybody gets nominal beam energies. And we're going to get to unprecedentedly low Q squared. So whereas PRAD stopped here, and this is log scale on the x-axis, PRAD 2 will go down here, some 10 to the minus 5 and some change, Jeff squared. We get a 3 times reduction in our uncertainty from being able to do event selection via tagging molar events, radiative corrections. That's something I don't talk about because people did the math better. It wasn't me. Detector efficiencies, we've got improved gem efficiencies by having 2. Beam background, we can filter that out with better tracking. High cal response through the improved electronics. We have better acceptance from the GEMS, beam energy inelastic, EP. These are model dependent uncertainties, and we just better understand them by going to lower Q squared. And so all in all, we had 0.0137 Fermi uncertainty for PRAD 1. We expect 0.0046 for PRAD 2. And so this is where we kind of expect to be in a few years once we finish the data and do the analysis. These are projected. They're intentionally put at 0.86 because that is right in between the 0.84 and 0.88 camps, so it's not choosing a side. PRAD 2 will have the smallest uncertainty of a lepton scattering experiment for the proton radius. Hopefully that will help close the book on what is the radius. Is it big or is it small? But now, getting back to fitting, we have our data. Now what do? we want the slope at 0 Jev squared. At 0 Jev squared, you have no scattering, so you can't actually measure that. So we need to just go as low as we can, fit it well, and extrapolate back to q squared of 0, which we do at least conveniently know is 1, so that helps us fix our normalization and helps you kind of choose what you're going to fit it with. And so at this point, say, how do you think we should do this? And we will go over here and hopefully this actually works. So we are going to fit the PRAD data. Thanks to Claude Code for writing this GUI for me. I had the fitting backend, but then it made GUI for me. So how would you fit that data? So we saw it, let me flip back there to see the data. We see a linear q squared, it's kind of like this, log q squared, it's like that. You had suggested a decaying exponential, so how about we try that? We can do e to the minus a times q squared and fit it. And so that gives quite a small radius, which is interesting. But we can see chi-squared is actually not too bad. That's actually surprising to me. I did not expect that. I've not played with that fit function before, so I had no idea what to expect. That's actually surprising, but right. So this gives you your fixed point at q squared of 0 is 1, and it fits the data, and you get 0.81. You can also then press this fit normalization button, and it allows the normalization of the two data sets to float so that they match better. And apparently this is pretty resilient to that. That's pretty interesting. Maybe we should try this. I'll have to run that up the chain. Anything else that anybody wants to try before I start just talking about what other people have done?
What about like 1 over x or something like that?
1 over x?
1 over q squared.
Yeah. 1 over, so we should have a fit parameter there, so it should be like a times q squared.
Yeah, whichever.
Yeah, a times q squared. And, oh yeah, that goes to, we'll go give it a, stop that.
Blows up, sorry, this bug.
Yeah, no, that's okay. We'll call that, it's because this initializes everything to 0, and so that immediately goes.
It still blows up at q squared is equal to 0, that's my bad. Didn't really think about that.
No, that's a fair point. I didn't think about it either. Trial and error. Anything else? Or should we just talk about what other people have done?
A dipole or something?
Dipole, yes. So that's 1 over, oh geez, that's 1 plus a times q squared, right? That's over parentheses, because I'm always fearful that it's not gonna. Yeah, so yeah, 0.82, which PRAD got 0.83, so that's actually pretty darn close. And that is a good suggestion also, because we always assume that ideal proton is a dipole, so that is what it was fit with in the past. Anything else? All right, let's talk about what other people do. So I had this in a whole bunch of things that you can play with. So if we look at this data, that is almost a line. If you stare hard enough, you can convince yourself that it's not actually a line. But what if we just fit it with a polynomial? We'll get small. Now, something that you could then do is we know that from the understanding of the proton radius is that it should be more or less linear at extremely low Q squared. The reason why we want to go to higher Q squared is so that we can then capture these moments, the other like higher order terms that maybe don't impact as much at low Q squared, but they're still going to impact at some level. And if you don't capture that that data very well, then you might not extrapolate well. And so we can kind of play with that and say, okay, well, what if we're really lazy and say we just want to fit this with a line? That's going to give you an extremely small radius. Nobody has gotten that from extractions before. And then if we say, okay, well, what if we only did the extremely low Q squared data? Say we only measured out to 0.01 and did it. You get a little bit closer, but you're still pretty darn small compared to world expectations. I don't think there are any theoretical expectations that it would be that small. And so we add in this higher Q squared data to better fit it, but then of course, you know, we have to have a more complex model because your Q squared blows up, you get an unphysical radius. You can do, and I'm gonna maybe throw a little bit of shade at the moment. Mine's a 1 data fit with a 10th order polynomial. And so now, caveat, this is fitting the PRAD data. Mine's data had a lot more point density. So whereas you know, clearly you see this dip right here, mine's fit doesn't have that. They have a lot of points in between this region. It's not going to do any of this wild in between point funky business. But you could then imagine that maybe when you go into your extrapolation region, if you go to a very high order polynomial, you might get some moments there or wiggles there from your high order polynomial. And so that's a concern. Doug Higginbotham, who I referenced before, had a paper from a few years ago that said, okay, well, what if we do polynomials, but then say that we want it to extrapolate well? You can then try and make it so those higher order terms kind of play off of each other so that they don't go too wild when you go outside of your fit region. You can say, what if you force the signs to alternate? So if one term is negative, the next term has to be positive, and just do that. Suddenly, that actually doesn't give what I thought it was going to give. It didn't. He did it with 11th order, so maybe that's why. Okay, well, pretend that behaved well because it was supposed to. But you can then, a little embarrassing because I didn't play with the 10th or 11th. I just for funny business, I went to very high order before, and you get, you know, unphysical if you go to very high polynomials, you alternate the sign, and suddenly you get something very reasonable with an extremely high order polynomial. And so that's kind of fun to see how putting physical restrictions on it just should be smooth-ish works. You can also do this Z transformation thing. This is a technique often in, I believe, Meson form factors, if I recall correctly. And this is a conformal mapping of Q squared to this Z parameter in complex plane. And don't ask me anything more about that because I will say it wrong. But what it does is you get into this Z space and you can put a cut on it so that everything is below the 2 pion threshold. And mathematically, you can show that while we don't have the exact functional form of, or while we don't have the exact GE when you do that transformation, you can show that the exact GE can be exactly represented as a polynomial in Z space. So that is a technique that's often suggested, and you know, you can get wild with it. And if you have a lot of terms in your polynomial, of course you're going to get some wiggles, but you can then put some very You can put some bounds on your parameters that are model dependent, but models that are not hotly contested. And you can then say, okay, well, they suggested, I think, that it shouldn't, no term should be really larger than 10. They said they would go for, people that suggested this said they'd go for 2, but if you really want to be careful, you can say 10. And so this, what I've done here, this says that it puts a soft boundary on each of the parameters, that it shouldn't be, the absolute value of it shouldn't be more than 10 with Gaussian distribution. So you can get a little past 10, but you penalize your chi-squared. And you can see that then you really do fit the data quite well, and you get very close to this proton radius that PRAD got. And so this is kind of cool because it really shows that when you play with these different fitting techniques, everything still trends to what was extracted by PRAD, suggesting that it is a data-driven extraction because most of the at least physical fits give you a pretty similar value. Now, what PRAD did in reality was this rational function. So a rational function, and I'll write on the whiteboard, is so Rnm is just a polynomial of nth order divided by a polynomial of nth order. And so this is a class of functions that mathematically is shown to not go too tremendously off the rails when you extrapolate past the region of the data. It's not perfect, but when we don't have an exact functional form for GE, that's pretty good. And so this is what the PRAD result actually was this rational 1-1 function. And if we go there, yeah, fits it pretty well. Pretty low chi-squared. And if you really want to go crazy, you can add more terms, and you know it'll go all over the place if you play with it. But one of the things is when you add more terms, you really need more data to constrain it. And so we said, okay, well, this kind of optimizes the spread of the data with how many parameters we have and gives you the most precise extraction that's not going to change too much based on the data. A paper came out prior to the PRAD data being even recorded that took a whole bunch of functional forms and said, okay, we have all these models of the electric form factor. Let's fit it with these different functional forms and see what functional form is the most robust. If we have all these models, they tell us what the radius is of that model. So can that functional form reliably extract the input radius of any model you throw at it, and to what precision? And of all of the 7 or 8 models tested and like 20 something different functional forms tested, rational 1-1 was far and away the most accurate for the most models compared to anything else, with the least like spread based on Monte Carlo simulations of that data. Yes.
Did you have like a extra systematic that was like related to the functional form that you chose, or was it just like once you chose it, that was the one that was good, or did you like have like an extra systematic uncertainty added to that?
Don't remember. I think I agree with you that there should be. I just don't know if there actually was one. So, right. So we've gone through a whole bunch of fitting, and I am over time. So let's go back to the summary and just. Okay, cool. So progress has been made on the proton radius puzzle. Tensions between the data sets are still there. We need to take more data to better understand this. Some pieces are untested, and I say untested loosely. There are people actively working on it at Muse and other places. We just don't have results. Experimental design trade-offs, you really, when you have something you want to measure, you should think about the trade-offs of what goes into it and really just kind of design the best experiment for what you want to measure in the way that you want to measure it. There's more than one way to do an experiment, and you just gotta say, this is what we're doing, and be aware of the consequences of those choices. PRAD 2 is running. It's an improvement on PRAD 1. Want to understand electron scattering, and we're going to have the most precise electron scattering result. And hopefully in a couple years, the data should be done. And like, so gotten a lot of questions because we had interactive stuff, but does anybody have any other questions you want to ask? Or do you just want to go to dinner and stop thinking for the day?
Yes.